Hello, I'm Omnik. I will be doing third division Califorce round 1047, and I will try to explain what I'm doing along the way. For once, I'm starting on time. That means that I will have to wait when everybody tries to open the problems. Problem A, Collatz conjecture. You're doing a research paper on the famous Collatz conjecture. In your experiment, you start off with an integer x and it uses the following procedure k times. If x is even, divide x by 2. Otherwise, set x to 3x plus 1. For example, starting off with 21 and doing the procedure 5 times, you get 21, 64, 32, 16, 18, 8, 4. After all k iterations, you're left with the final value of x. Unfortunately, you forgot the initial value. Please output any possible initial value of x. Okay, so we are given the number of iterations and the final value. But the final value is up to 20 and the number of iterations is also up to 20. I can just take x multiplied by 2 to the power of k, right? Like, in the all k operations we will do, x will be even and we divide it by 2, so after k iterations it will be divided by 2 to the power of k and the result will be x. That's funny. But I guess like what I wanted to say before that is that like the smallest the number can get is like b divided by 2 to the power of k, so our initial number must be at most 20 million, like ish, or like 20 multiplied by 2 to the power of 20. So one can like try all the numbers, do the k iterations, and for every number up to 20 just remember what was the starting value to get there exactly k iterations. So that would be fast enough. I'm not sure why they didn't like bigger limitations, like x up to, I don't know, a billion and k up to 30. If just x multiplied by 2 to the power of k just works, that would be... Well, they probably wanted to allow the opportunity to solve the problem even if you didn't get the funny solution. But yeah, that's a great problem A. Like, problem there is a big issue of coming up with like the easiest problems in the contest, because like they should still be problems, right? Like it shouldn't be just obvious what to do. Otherwise, like what's the point? But they must be easy enough for a lot of people to solve. And this is great. This is great. K and then x. Yep, this looks good. Problem B, fun permutation. You're given a permutation P of size n. Your task is to find permutation Q of size n such that GCD of pi plus qi and pi plus 1 plus qi plus 1 is at least 3 for all valid I. Okay, I guess we can just make all the elements in the sum to be n plus 1, and then all the GCDs will be n plus 1, which is at least 3, right? Just for number x in the permutation p, print n plus 1 minus x. It also will be a permutation, and all the sums are n plus 1, so very good. Problem C. Maximum even sum. Given two integers a and b, you are to perform the following procedure. First, you choose an integer k such that b is divisible by k. Then you simultaneously multiply a by k and divide b by k. Find the greatest possible even value of a plus b. Okay, so like the product of those numbers will stay the same because we multiply one by k and divide the other by k. We want to maximize the sum while product stays the same. That means that we want to make those numbers as far from each other as possible, which would like ideally we want to just choose k equal to b, and then we will get a times b and 1. But maybe that value is not even. It will be even if both a and b are odd. Then their product will be odd, and we are good. If the product is even, then since the product stays the same, one of two resulting numbers must be even. So we want both of them to be even. Well, I guess if b is odd, then it's impossible. Otherwise, well, because after dividing by something, it will stay odd. So we cannot make both of them even. Otherwise, we want b to be even and a also to be even, and for them to be as far apart as possible, which means that we want b to be equal to 2 after the division. So just take k equal to b divided by 2, and like maybe a will still be odd, but then it's also impossible because in the product prime divisor 2 appears only once, so we cannot make both summands even. So one of them will stay odd, and that's bad. Otherwise, one of them is 2 and the other is ab divided by 2, which will be even if it is at all possible, and that's the maximum we can achieve. Okay, that's just some like odd even case analysis. Semi not very interesting, but well, not every problem can be Collat's conjecture, apparently. So if both of them are odd, then the maximum value we can achieve is a times b plus 1. Otherwise, if b is odd, then it's impossible. Otherwise, I want to have a times b divided by 2 and 2. So if a is still odd, impossible. One 658 74. That looks correct. Problem D. Replace with occurrences. Given an array A, let f of x be the number of occurrences of x in the array. You have an array B of size n. Please determine if there is an array of size n such that f of ai is bi for all I. If there is one, construct it. So we are given an array of number of occurrences of every element, and we need to construct one. Well, that's very simple, right? Just for every number, look how many times it appears. Number x must appear some number of times that is divisible by x. Basically, if in the array A we have some numbers that appears x times, all those appearances will be replaced by x in array B. So we just in the array B we need to split all the occurrences of some number x into groups of size x. If such split is impossible, then it's impossible. Otherwise, just assign different number for every group, and that's it. Okay. So far, A is the only problem that is good in some sense. I mean, those problems are fine. They're just well, what I said, like it's barely a problem. Like it's obvious what to do, but problem A was not like that. Actually, I don't need this. So for every given number, I want to have the list of positions. If the number of such values is not divisible by x, it's impossible. Otherwise, like I need to split it into groups of size x and put different numbers in the answer there. Problem E, Maxification. You're given an array A of size n and an integer k. You do the following procedure k times. For each element AI set, you do the following procedure k times. For each element he sets AI. Who's he? Sets AI to max of all the numbers except AI. In other words, sets AI to the mix of all. Yeah, what I said. This is done for all elements in the array at the same time. So, like, we have an array, we calculate maxes without every element, and then like replace all of them at the same time. Please find the sum of elements in the array after all k operations. And I'm assuming k is very big because this operation looks very simple. Maybe not, actually. Okay, when I see yet another problem about max, the first thing I do, I think about, like, what if, like, the max is 0? So in this case, it means that what if there are no zeros in my initial array? Then after I remove some elements, there's still no zeros, so the max will be 0, right? It means that after one operation, all the numbers will become zeros. Then all the numbers will become ones. Then all the numbers will become zeros, ones, zeros, and so on. Okay. If I have all zeros, it's the same thing. I already understand what happens to the array when all the elements are zeros. But what if okay, I guess I will actually need to write something down. So okay, for every element, you can look at all the occurrences. Also, I guess it's maybe helpful to understand that if we have two positions that are equal, then they will stay equal forever, because, like, removing that element is the same as removing the element in position I is the same as removing the element in position j from our multi-set of numbers we are counting max on. So, like, they will be replaced by the same element. So we have some positions of zeros. Right? Oh. Some ones. Maybe like 1, number 2, 1, number 3, several 4s, and so on. But then m is the first number that we don't have any occurrences of, so, like, this m is the max of the whole array. So what happens when we remove some other elements? If we remove an element that is, like, greater than m, nothing will change because the max will still be m. What if we remove, like, this element? Again, nothing changes because, like, we have more than one element equal to 1, so the max will still be m. But if we remove the element that has only one occurrence and it is smaller than m, then the max will become this element. So if m is the max of array, for many elements we will replace them by m, but there will be some numbers such that xi is smaller than m, and there are no other occurrences of that number. Then those numbers will be replaced by themselves. So we will get x1, x2, xk, but all other numbers will be m. Okay. What will happen next? Well, in this situation, if we have like several zeros, now in this array there are no zeros. So we'll get all zeros, then all ones, then all zeros, and so on. But what if 0 was one of those numbers? Well, basically, I want to apply kind of the same logic to the second transformation, but now I know that I might have like a lot of occurrences of m, although I guess it is possible that there are no occurrences of m. But in general, what I do know is that for all numbers that are smaller than m, there is at most one occurrence of those numbers. So, like, after the first transformation, I will have, like, at most 1 0. So, there is a position of 0, a position of 1, and so on. Maybe there is, like, the first number k that has no occurrences. Then there are some numbers, then some number m that can have many occurrences. But then all the higher numbers do not have any occurrences, because all those xi's that stay the same, they are smaller than m. So what can happen? I might have like some numbers that are so let's say that k is smaller than m, and so there was some number k that is smaller than m that did not have exactly one occurrence in the original array. Then like something similar will happen. So numbers from 0 up to k not inclusive will stay the same, and all other numbers will be replaced by k. Yes. So after so after the first iteration, I will get something like this. Maybe there is no such number k, and like all the numbers that are strictly smaller than m appears exactly once. But after the second operation, if it was like this, then it surely will be like, if we have a situation like this, then after the second operation, all the below k will stay the same, and now k will be like appearing many times probably. So after either 1 or 2 or maybe 0 iterations, I will surely have the situation when there is m that can have many occurrences, but all the previous ones occur exactly once. And nothing greater than m occurs. So this situation is, I guess it's kind of similar to what was happening when it was like all zeros. Just like these guys will stay the same, like up to m, but then all of the m's will be replaced by m plus 1 if there are any. And then all the m plus 1s will be replaced by m, and so on. So those numbers will stay the same, and those two will change places every time. So I guess the simplest way to solve it would be like to just apply the operation trivially 2 times, and then I know that I will have some elements that appear once, and then all others must be either m or m plus 1, and then they will switch places, and by parity of k I will just determine what is the final state. It's interesting that they want the sum, like could have printed the array. Maybe they didn't want to show the answer to the sample. Actually, what will be the answer to the sample? 0, 1, 2, 3, 4 appear exactly once, so they will stay the same always, and the remaining 3 elements will be either all 5s or all 6s. I guess it should be all 5s, right? So the sum of those is 10, and then plus 3 times 5 is 25. And if it was 8 here, it would be 28. Okay, I guess. Okay. That is a big jump in difficulty. maybe I'm missing something obvious, but I mean, you still kind of need to understand what will happen. So I guess that's the simplest thing you can do. Do I actually need this? No, I don't. Okay, so 2 times I just want to apply the operation in linear time. I need to be careful because k can be 1. So if k is 1, I just want to apply it once. Let's just write it like this. If k is 1, do the operation and then just count the sum. otherwise I will do the operation twice. Well, technically I should say like k minus equal to 2, but that doesn't change the parity, so I guess I can just say like if k is odd, then do the operation one more time and then just print the sum. Okay, so I don't even need to carefully do anything, just understand that it will cycle after 2 applications. So to do the operation, I will count the number of occurrences of every number. I think it is guaranteed that they're bounded by n, but like, to be sure, I will do the increment only if it is up to n. So now I want to find the max. So max is n. And now if AI is greater than m, or it appears more than once, then the number will be replaced by m, otherwise it will just stay the same. So that's it. Okay, maybe it is considered like guessable, because apparently a lot of people do not care about solving the problems. They just want to write something that passes the sample, and that's why it's considered like not a hard problem, because the solution is very simple, but actually proving that it works is not that simple. Okay, problem F, prefix maximum invariance. That's a lot of words. Given to arrays x and y both of size m, let z be another array of size m such that the prefix maximum at each position of z is the same as the prefix maximum at each position of x. This definition does not utilize y at all, and also like it doesn't define the array z. Z is just some other array that has the property. But okay, for example, that can be x. Obviously, they will have the same prefix maximums. Okay, let's read further, but like this is just a bad way to write the statement, right? Formally, maximum of x on prefix up to I is the same as maximum of z on prefix up to I. Okay, define f of xy to be the maximum number of positions where zi is equal to yi over all possible arrays z. Okay, that makes sense now. So, but like, given two arrays x and y, f of xy is the maximum number of positions where zi is equal to yy over all arrays z such that this happens. Like this definition is written like backwards. Like you kind of define array z, which is not the definition, because it's like not well defined, and then you explain what that's very bad. Okay, you are given two sequences of integers a and b, both of size n. Please find the value of. So we choose like subsegments and then calculate f over like subsegments, and then take sum of them. Okay. And n is big. Interesting. Okay, so for given arrays x and y, like what is this z that maximizes the number of positions where it is equal to y while not breaking prefix maximums? Well, it should be simple, right? Like we just for every position, if it is a new maximum, then it is uniquely defined. Like if in x it was strictly greater than everything before, then it must be the same in z. Otherwise, it just must not increase the maximum, so it must be less than or equal to the prefix maximum before. So if we can put it to be equal to y, then good. Okay. So that would already give us like n cube, surely. Probably n square is also simple because like we can fix the left border and then run to the right and find the optimal race for all the right borders at the same time, because like our greedy just works left to right, but we need to do it faster. I guess. Okay, I guess like I want to calculate for every position, calculate the number of times it is good. What does it mean good? Is it like actually basically it means that I can replace corresponding x with y without changing prefix maximums, actually just in this point. So we have A, have B, I'm now looking at some position. So I want to find for how many segments this position is good. What does it mean good? So like I fix the segment. Good means that if I replace AK by BK, the prefix maximums on the segment will not change. But if they will change, they will surely change like up to this point exactly. So I just want to make sure that so if this is the left border, then maximum over I from L to K inclusive of AI is the same as maximum of like the same thing except replace AK with BK and only that one. So we're taking the maximum on prefix of AI not inclusive, so K minus 1 AI, and also of BK. So if this is good, then this position is good for this segment. We can clearly notice that this definition of good does not depend on the right border of the segment, so we just need to like look at the left border and then multiply by the number of possible right borders, which is n minus k plus 1. Well, it will be n minus k because I'm using zero indexation actually, so this last one will be n minus 1. So Okay, how do I do that? I guess I need to like consider cases depending on how A and B are related. Although like they are kind of interchangeable in this definition, so let's just say that one of them is somewhere and the other one is somewhere else. If they're the same, then obviously it's the same because we're just taking maximums over all the same set of numbers. Um, so if we just take segment like this, it's bad if they're different because the maximum will change clearly. But then we move the left border and we insert some new numbers in the sets over which we take the maximum. And once we insert some value that is like here, so it's not less than both of those numbers, then we are good. Like if we take the number that is greater, then the maximums will be the same. If we don't, then one of the maximums will be like this number and the other will be strictly smaller. So I just want to find like the closest element to the left that is greater than or equal to maximum of those two numbers in the array A. And that should be easily done with like maintaining the like current suffix maximums in stack. Yeah, I think it is the simplest thing to do, so not even gonna try to make it simpler. It's already simple enough, to be honest. Okay, so I'm going left to right, maintaining that stack. So first thing I need to do is do the binary search on that stack to find the closest element that is at least maximum of AI and BI. Let's say that maximum is this. So L is position on the stack of that element. So if L is not -1, I need to add to answer looks good to me, except yeah, if they're equal then it will be wrong. I think I can just like update the stack first and then find the answer. So while size is greater than -1 and stack of size smaller than a of I, so it's minus. So even in the first, oh wow. Yeah, okay, that is not true. If they're different, I need to consider the elements before. So yeah, I guess I need to write separate if for that case. Yeah, now it's good. That's not a bad problem actually. And the last problem G, cry me a river. There is a directed acyclic graph with n nodes and m edges. Each node is initially colored blue. Let's define the fun graph game as follows. Initially a token is placed on node S. Cry and river take turns moving the token to a node such that there exists a directed edge from its current position to that node, with cry going first. So they're just moving the token through the duck directed acyclic graph. Cry wins if the token ever reaches a node with no outgoing edges after either player's turn. River wins if the token reaches a red node after either player's turn. If the players reach a node that is both red and does not have outgoing edges, River wins. So basically, Cry needs to avoid red nodes, although River can try to move to them. Since the graph is acyclic, it can be shown that the game always ends in a finite number of turns. Yes. Note that Cry and River can win the game immediately if the starting node S doesn't have outgoing edges or is red, respectively. You must handle Q queries of the following kind. When you update the color of node U to red, it is guaranteed that node U was blue before this update. And 2U, if a fun graph game is played with the token initially at node U and both players play optimally, does Cry win? Okay, so like we notice immediately that every node is initially blue and we change the colors to red, so like we only add red vertices. So like, it is it might be very important that the vertices only changed like their status in one direction. Maybe that direction is not convenient for us, but if we want, we can reverse the process and look at the queries from the end and change the nodes from red to blue if we need to. I don't know yet how I'm going to solve this problem, so I cannot tell right now. We could do like obvious DP from vertex and who's moving to determine who's winning at every vertex. But that will be like linear from size of the graph, and I would need to do it for every query. So that's slow. Maybe I can just like propagate, like when some node becomes red, it can cause some previous nodes to also become winning for river. Yeah, I guess. Like, I was planning on doing DP on the DAC, the states as a vertex and whose move it is. And like the position is winning for the player if like it might be like winning immediately, it might be losing immediately, but if not, then we will look at the moves from that vertex, and if there is a move to the position that would be losing for the opponent if it was their move in that vertex, then we would win in this position. Initially, all the positions are winning for Cry because there are no red nodes. There's literally no situation where Cry can lose. But then we will turn some nodes red. That will change the status of, well, at least like when we stay in that node, we know that river wins. But maybe for some previous nodes, now river can also win in those situations, like depending on who's moving and so on. But like we can try to propagate that information using backwards edges, and we understand that the states can only become like winning for river because the situations gets better and better for river. Like we turning more blue nodes to be red. So the only thing that can happen is that like some state was winning for river, but not anymore. Now it's winning for credit. Not anymore. Now it's winning for river. And that can happen only once for every state. So if we just carefully do this kind of like retro-analysis, BFS type of thing, like visiting only every node once, we will be good. So that's what I will do. Interesting. I like it. It's such a natural concept, but I don't think I have seen the game. Which like basically you are given like the straightforward implementation of like game on directed cyclic graph, and then you repeatedly mark some nodes as winning for one of the players, and you are asked to reanalyze the game. I don't think I have seen that before. Pretty cool. Since I'm doing it as a BFS, kind of, I don't think I need to find like topological ordering or anything. I will reverse all the edges because I need to go like backwards through the graph. I will just use 1 for cry winning and 0 for cry losing, like independent on whose move it is. Although like this ans is for vertex and who's moving. It's like I will still need to handle them separately, so it like I just need to choose one notation and stick to it. I don't think one will be like, much more convenient than the other, and for this one at least I will be able to just cry always starts, so I could have used like one for if the person who's moving in this position wins, but yeah, I will be able to just write if ans v0 print yes, else no for queries. You need to inverse the edges. But for vertex v from which the edge was going, I will increase the degree. I need this for the states when cry or the first player moves in this vertex, because this vertex will become losing for them if and only if either it is just losing, it is just red, or all the other vertices that can be reached by an edge are also losing for cry if river moves in them. So I will when some vertex becomes winning for river when they're moving there, I will look back to all the vertices from which there was edges there and decrease this degree, and if it becomes 0, then when its cry moves in that vertex it will become losing, and I need to mark it as such and add it to the queue. This is just basic retroanalysis, but it's just basic retroanalysis. Following M lines contain edges, and then Q lines, type of query, and a vertex. So the query of type 2 is does cry win, so that's just if ans v0 print yes, else print no. But here Marculus v0, Marculus v1. This is just a helper function. If it's already marked as losing, I don't want to put it in queue again. for this, I just need to look back. So if k was 0, it means that in this situation cry was moving, and so when one step back river will be moving, and since this state is losing for cry when they're moving there, this state will become winning for river right away. So just mark lose u1. But otherwise, I'm doing what I said I will be doing, decreasing the degree, and if the degree becomes 0, then mark lose. Okay, that should be it for this contest, assuming that my G passes. It was a pretty good contest. Like, well, I said that those problems were kind of boring, but well, I'm not the intended audience, and they were fine for their positions. Some problems are nice. G is nice, F is nice, A is absolutely brilliant. Yeah, pretty nice contest. Thanks for watching. Bye.